Greetings! Here's part 5 of assembly language on the Motorola 6800. We've pretty much touched upon many aspects of it: the machine or assembly language itself, the environment we use to run it, whether it's under a pure simulator or something that actually simulates a commercial device that in the old days allowed you to run 6800 code. For those of you watching, or who have watched I should say, you'll notice that there's a slight change in the simulator window, and that is we no longer have the picture of the Heath Kit ET3400 trainer here, but rather a new window, which I'm sure most of you can guess what this is for. What I've done is I've added to the simulator some extra code that lets you simulate there's an expansion unit for the trainer called the I/O memory expansion, and I've tried to make the simulator not only simulate the base trainer, but also the expansion. What is contained in the expansion is it bumps RAM memory up from 256 bytes to 4K bytes. Woohoo! It also created some new memory address space for more ROMs. This has a 1K ROM to simulate the trainer, but with the expansion there are two more ROMs available. One is an advanced machine language monitor called the Phantom 2, and then there's an implementation of Tiny Basic. The most significant upgrade is that the expansion has a serial port in it, because both the new monitor and the basic interpreter cannot possibly be run on a 6-digit 7-segment display. So what you do with that, once you had that installed, you hooked it up to a terminal and you typed away on your terminal rather than the hex keypad, and you received your output through the terminal rather than the 7-segment displays. So what this window is a poor attempt at trying to simulate a dumb terminal. I spent not too much time on it to be able to show basic operation, but let it be said that I was unsuccessful in getting it to work fully. But let's see which parts of it do work and what it does. So the very first thing we got to do is go and say apply serial patch. And I'll explain why I had to patch the code once we have a look at what the serial port looks like in hardware. Then we run the trainer itself, and we're all familiar with that. But now let's go into the Phantom machine language monitor. For that we use the do command, and we go to 1400 hex. And we get a message that says monitor. Well, it's the monitor prompt. And now we can do all sorts of things. And again, I did this quickly, so it's a bit clunky. You have to enter your commands down here and then click the send key, but let's use the I command, which stands for instruction, and we can give that an address. Let's do FCOO, which is the entry point for the original firmware. And what this does is it does a machine code. It shows us the machine code, but it's smart enough to know that the opcode of 8E over here is followed by two more operands. So what that does is it doesn't disassemble into assembly language, but at least it knows how many bytes are required for every instruction. Now I think what you can do with this is give it a range, and I think it'll disassemble a few instructions, but well, kind of. It got confused. And I think the code's running correctly. I think the way I'm handling of intercepting the serial stream wrong. But quick overview of that, you can do a dump memory. Let's see how that one works. Let's do a dump 0 to 8. That one actually worked. Let's see if it's lying. Let's point the memory window at something that's non-1. And then let's have this thing dump FC10 through FC1F. Let's see, did it do 1F? I guess it stopped. No, yeah, it did. So it shows the address over here, and then it shows the memory contents. There's also a dump memory command, which will let you alter memory. So let's see. Oh no, that's already dumped. That's the memory command I'm talking about, and the new one. And let's do FC20 through FC1A. And we forgot the comma. So yeah, on this one it also seems to lose its mind. It's almost like it goes in, scans, yeah, I mean we can see it here. It scans the first part up to the comma of the command, displays that, then reads the end address, and then displays one more memory location. Well, you can already see that if we're using hardware with a working terminal, it would make diddling with the memory and stuff like that a whole lot easier than having to use this keyboard. If I spent a whole lot of time on this, I mean, I have all the tools. I can basically step through the code and see why it's acting up over here. But I'm going to save that for the day when I have actual hardware. And instead of spending a lot of time on getting the simulation of the serial port running, we'll just wait for that, because this is a bit of a fool's errand. But as you can see, it's basically sitting here. It is reading the state of the serial of the receive line over here. And the receive line value is in bit 8 of location 1000. It's doing a branch plus, which means that bit 7 is 0. And the minute that bit goes high, that means we've encountered a start bit, and it will start actually reading stuff from the serial port. So what's remaining is the second extra ROM, which is a basic interpreter, tiny basic, and unfortunately that just doesn't want to work. I'll get a peep out of it, but that's about it. The way to do that is we use the go command. We're still in the phantom monitor, and we go to 1COO. So what you can see it did, here's our go 1COO. it ignored the carriage returns here and then prints out HTB1, which stands for Heath Get Tiny Basic 1. And hard to see, but over here, that's the prompt. So now what we're supposed to be able to do is enter commands. But here's what happens. Let's try a real simple one. Trying this. And as you can see, it goes bananas. It keeps going all over the place. And finally it crashes over here in an invalid instruction, somewhere in RAM. Like the machine language monitor, I'm sure I can fix it. We got all the tools here. All I got to do is single step through it and see what's ailing it. But as with the machine language monitor, I'm going to wait on this one till I have actual hardware. Thought it would be interesting to have a look at the schematic of the expansion box, and specifically the RS-232 part, because it's not done what you would generally expect. Generally, you use an IC, in this case most likely the Motorola 6850, which is an asynchronous communications adapter, and that one handles all of the nitty-gritty of serial transmission for you. You give it a data byte, and it will format it and send it out at the proper baud rate, while at the same time it receives all the stuff that's coming in that's being received. So when a new byte is coming in bit by bit, it builds a new byte, and once the new byte is built, it is ready for the processor to read that byte. So it's a relatively simple I/O operation for the processor to get serial, to send and receive serial data. Another thing that the 6850 can do is, in order to provide you with a maximum throughput, it has an interrupt output that will tell you when either the transmit register is empty, which means it's ready to receive a new byte from you, or when the receive register is full, which means a new byte has arrived and you can read it. So when you utilize the interrupt structure of that chip, you can basically maximize your throughput, your serial throughput. Now here's what Heath did. So they used a Motorola 6821 PIA, parallel interface adapter, which we're looking at right in the middle over here. So it's just what the name says. It has two 8-bit bidirectional ports. PA0 through PA7 is port A, and PB0 through PB7 is port B. And on the other end, we just see our regular interface to the system bus. We have the data bus coming in. We have the lower two address bits selecting internal registers. Registers can be either data registers to read data, or control registers that tell this chip how to function, whether a bit is an input or output. And additionally, there's a read-write pin. There is a reset pin, which is tied to the processor's reset pin, and that just puts it in a known state. And we got a clock input over here. That's pretty much it. It does have two special purpose bits, CA1 and CA2, which can be used to generate interrupts and look for transitions on outside lines. But as you can see, none of that is used. Here are the interrupt outputs of it. Two more single bit general purpose input outputs. But the interesting thing here is this doesn't have any smarts as far as being able to format bytes into a transmit bit stream or assemble an incoming bit stream into a total byte. So, and I'll tell you why I think they decided to use this, but the interesting thing is, because of what I said previously, is they use a process or a method called bit banging on this to create the serial stream, and I guess reverse bit banging to detect the incoming data. And the way this works is port A bit 0 output is set as an output. So this is basically something the processor can change from 0 to 1 and vice versa. But the processor has to time this. So this is very much like drawing an image on an Atari 2600, and then the processor has to do all the timing to take a byte of data, separate it into bits, and then send the proper bit level out for the proper amount of time for a bit clock for the other side to recognize it and receive it, and then of course reassemble it as a byte it's received. On the other hand, the terminal, which is the other side, sends bit streams back to this, which in this case are received on pin PA7, which is configured as an input. And all this does is it reads the state of what's coming in. So the processor again has to sit there, read what's coming in on here, figure out how to sync this, basically sitting there waiting for a start bit. I think the way it does it, I briefly looked at the code, but it sits there, and as long as this is a stop bit, i.e. it's in, I think it's a low logic level, it thinks that the line is idle. The minute a start bit is generated, this line jumps high, and it is assumed that a bit stream for a byte is going to come in. And then it pretty much applies the same timing that it applied to when creating a transmit stream and assembles an incoming byte. Well, actually, this doesn't. This just passes this bit on to the processor, and this bit is set by a bit from the processor. So the process, it's done in software. The serial communication, the low-level stuff, is done in software using a method called bit banging. And as you can imagine, it gets a bit hairy because the processor can't really do anything else, because otherwise the timing will be off and it'll drop bits and bytes and all of that. But I guess it was deemed to be the best usage of hardware to use a PIA rather than an asynchronous serial controller. The only other thing that this is used for is we also generate, let's see, yes, we also generate cassette signals in the same fashion using port bit 0 and port bit 7, and it uses a Kansas City interface, or standard, which was a standard used for writing to cassette in the early days. And other than that, all it uses really is ports A1 through A4, even though A4 is tied low permanently. And these jumpers are used to set the baud rate. So on the Heath kit, they didn't even put a dip switch in, but you have to hardwire these jumpers. The processor comes in and reads these bits, and depending on the state of the three jumpers, does a table lookup and goes, oh, you want 110 baud. All right. so be it. It's not used for anything else. So that still doesn't make a whole lot of sense to me, because you could have created a monitor command to set the bit rate and ended up using, with a 6850, much simplify what the processor would have done. And I don't think there was a huge price difference between a 6821 and a 6850. So to me, that's a bit of a mystery, but what do I know, right? And that pretty much gives you an idea of what the expansion looks like. It's got a bunch of RAM over here. It's got the extra ROMs. And power supply down here. And other than that, nothing overly exciting. One very important resource for doing 6800 programming is this manual, the M6800 Programming Reference Manual. It is available for download. Somebody scanned it very nicely in PDF form, and this pretty much contains everything you'll need to know about the processor in a compact form. For instance, here we have a description of the registers, and it talks about some of the peripheral chips, the 6830, the 6810, which is a RAM chip. Tells you how to program the 6820, which was the predecessor to the 6821, which we just looked at. But most importantly, let's look at the description of the instructions available. And for that, let's pick Add, if I can find it. And that is there's an add carry, and there's an add without carry. So let's look at that one here. It tells you the mnemonic of the assembly instruction over here. Down here, it tells you what the addressing modes are possible for doing an add. So as you can see, you can do adds. There are 4 different modes, addressing modes, for the accumulator A and accumulator B. And they do the same thing. The only difference between the first 4 and the last 4 is that the first 4 basically put the result into accumulator A, and the last 4 put the result into accumulator B. In this column, it tells you the number of machine cycles required to execute this instruction, how many numbers of machine code, what is the number of bytes total for this instruction, including the opcode. And then it tells you what the opcode in hexadecimal, octal, and decimal is. This is interesting. I guess this manual is old enough that they're still listing stuff in octal. So, the big question is, what is 253 in hexadecimal? Well, as you can see, these 2 representations of the decimal number 171 couldn't be any more different. But in episode 1, we talked about number systems, so it's all there. It then tells you another very important part, and that is what condition codes are affected and how they are affected. And it pretty much tells you straight off what causes how the value is determined for these. First of all, verbally here, the C flag, for instance, said if there was a carry from the most significant bit of the result, cleared otherwise. It's an overflow bit. But down here, they give you the Boolean equations for how to calculate that. which is very useful when you're writing a simulator. And all the other instructions are explained, are listed in a similar form. And with this, you can pretty much go through this list and see every instruction available. The thing we looked at earlier was there's also an add with carry. And you'll notice that it's very similar, except that the operation says accumulator X is equal to accumulator X plus the contents of the memory of the addressing of the memory location used, depending on the address mode. But if a previous instruction generated a carry, that is also added to it. So an overflow bit from a previous add will be added to the result. And the usefulness of this is if you're doing multi-byte additions. What you would do is, let's say you only wanted to use the add carry and add up, and add two, let's say, 32-bit numbers, which are 4 bytes. Well, for the first add, you would manually use the clear carry instruction to make sure, because there's no, when you are adding something to the lowest byte, there is no carry from a previous instruction. And you're basically going to do 4 adds, but for the 3 subsequent add operations, you will just use the carry that was generated from the previous one. And your result will be a proper multi-byte add. There's also subtract instructions, there's subtract carry instructions, which should actually be called subtract borrow properly, and a whole slew of other instructions, which you can scroll through, and as you can see, there's a compare instruction, tells you what it does, the flags, the codes. All in all, probably the most useful document you will ever need to do 6800 programming. There are lots of books, third-party books on this that give you code examples, which is very useful and will help, but you need to start with this document. Well, that was a lot of fun. I obviously underestimated how much time it would take to even scratch the surface. There's no way we can go through every single instruction in a video because of time limitations. But I think the 6800 is a very good place to start, if you're interested, of course. One question I am sure I will be getting, if I haven't already, is where's the source code for this wonderful animal? Well, the source code's sitting on my machine, and it is not ready for prime time. So what I'm getting at is I will not be publishing or releasing this into the public domain for a while. And the reason for that is not that I'm stingy or that this is going to be a commercial product, but I basically wrote just what I needed. And I'm probably the only person in this world who can use this productively at this point. It needs a lot of cleanup, and all I'm going to say is it's not ready to be put out in the wild yet. There's a lot of interest for this. I'll spend more time on it. I'll clean it up and fix up the serial window. But for now, please don't ask, because it doesn't make a lot of sense to release this. As I mentioned before, please consider donating if you have something in your closet or attic or wherever. If you want to see more content, that is going to be your ticket for me to go and make more episodes. Because as I said, I'm having a hard time finding candidates that are interesting enough to make a video for. But thanks for watching. You already know the drill. thumbs up, comments, subscriptions, all that good stuff. And let's see what I can cook up for you for the next video. Bye.